let's look at the mass that an atom or nuclide actually has. Let's pick our chlorine 35, which is one of the isotopes of chlorine. Now, the mass number is giving me the total number of protons and neutrons in the nucleus. But if I actually measure the mass of the atom, I get not 35, but 34.96885. So don't confuse these two things. The actual mass of the isotope and the mass number are not the same thing. This one is an integer that counts particles in the nucleus, and this one is an actual mass measurement, so it's going to be a decimal number. So that's one big difference between a mass number and an isotope mass. Now, there's something else that is disturbing about this, because if your protons and neutrons in here weigh about 1 atomic mass unit, and they actually weigh a little bit more than that, you would expect that this would be a bigger number than this one, than 35, that this would be over 35. And this one only includes protons and neutrons. It's a count of them. This one includes the masses of the protons, the neutrons, and the electrons. Let's figure out, if you totaled up the mass of all the separate particles, the protons, neutrons, and electrons, what this number should be. And we get something that's surprising and extremely important. Here's the mass budget. Now, I know how many particles are in here. We counted this one before in another video. There's 17 protons because the atomic number of chlorine is 17. And here's the mass of each proton. There's 18 neutrons. I could subtract the mass number minus the number of the atomic number and get 18 for the number of neutrons. And here's the mass of each neutron. There should be the same number of protons and electrons if it's not an ion, if it's a neutral atom. And the electrons weigh much less. Here are the weights for each one. So if I take 17 times this plus 18 times this plus 17 times this, I get this. Now look how much bigger this one is than that one. Let's figure out what the difference is between those two. I took this number minus 34.96885, and I get something I'm going to call the mass defect, the difference between those. It's too light. There's some missing mass, and this is the amount of missing mass. Now, where did it go? It turns out that if you're going to try and crunch 17 protons together in a tiny nucleus, they're going to want to kick off of each other. They repel because they're all positively charged. The nucleus should fly apart, and the pieces should spread out at the speed, close to the speed of light. They're really going to go fast. This is going to not just fall apart, but it's going to explode. There must be something that holds the nucleus together. And there is. There's a force called the strong nuclear force, and there's an amount of energy that is used to hold those protons together. You've seen this equation before, but you may not have realized what it really says. This is kind of the key to nuclear energy. This mass defect is actually the m in this equation. This is actually the binding energy for the nucleus. It's how much energy is binding the nucleus together. Now, I'm not going to ask you to do calculations with E equals mc squared. What's important is that you know that the isotope mass is less than it should be because some mass is lost in order to bind the nucleus together. And that's another reason why these two things are different and why this and this number are different too, because of that binding energy. If you had ignored that tiny little discrepancy, that mass defect, you would miss the whole thing about nuclear power. I mean, that's how nuclear power works. You're releasing some of that binding energy there.